the background about this very humbling prize. Thank you for the opportunity to speak in this venerable institution, and thank you for coming. And thanks for bearing with me doing this in English. I just think it will be easier for me to speak, and I think it will also be easier for you to understand in English the subject that I want to talk about tonight. And this is about the encounter of two fields of physics that normally don't really encounter each other very much. And that is quantum physics and the physics of sound and vibration, or more generally about the motion of relatively large objects. And as a background, quantum physics, you know, to some degree actually originated in this very town, in the discussions, you know, of this very hygge setting here with beer and coffee, of Niels Bohr and his young colleagues, one of which here in the picture was Werner Heisenberg. And they may have been discussing, you know, the mathematical theory, but also the more philosophical and to some degree bewildering features of quantum physics. And I want to tell you about those a little bit. One of the features that was surprising, given everything that has been known about physics to that point, was that measurements all of a sudden had fundamental limits in how precise they could be. And Heisenberg was one of the first who could formulate that in a very specific mathematical form, but he also illustrated it in actually a quite nice thought experiment, which is now called the Heisenberg microscope. So he actually published this in a paper while he was in Copenhagen. And the idea is very simple. So he said that I'm a physicist and I might want to know where an electron is. And I call this position of the electron X. And if I use a microscope to do that, well, I have to send light onto this electron in the first place, and then I can collect the light through a lens onto a screen. But on the screen, the blob that corresponds to the electron will not be infinitely small. It will have a certain size. It will be sort of washed out a little bit. And the degree to which it's washed out, he called the uncertainty in the position, delta X. And he realized that that's not the only uncertainty that exists in this problem. Another uncertainty pertains to the velocity of the electron, or its momentum, p. And this velocity of the electron, its momentum, is also influenced by the light that is used in this microscope. And the uncertainty that I have about the velocity of the electron, delta p, is related in a very fundamental way to the uncertainty in the position, in that the product of these two uncertainties must be larger than a fundamental constant, than Planck's constant, the reduced Planck's constant over 2. So there is a fundamental limit in how small the uncertainty of these entities can be, and this is the Heisenberg uncertainty. And that was really a new feature that is unknown in classical physics. But it gets even a bit more strange. So in quantum mechanics, actually, we're describing the state of an object with a wave function, which is actually a mathematical object that, you know, describes everything that we know and can know about this object. It's a little bit similar to a probability distribution, but not quite. It's actually probability amplitudes. But it has an important feature, which is it can, for example, describe the state of an object to occupy two states at the same time, or to be very literally in two places at the same time. And that may sound quite bizarre, but it took, well, a few decades until the 90s that people like David Wineland and his group in the United States could show experimentally that this is really the case with single atoms. I can't go to the details, but they did experiments where they trap a single atom in a vacuum apparatus, manipulate its motional state with laser beams, and they could show that it's possible to prepare this single atom in a state where it's at two places at the same time. So that's really rather bizarre, and that's certainly nothing that we encounter in our world of large objects that we can, see with our eye. So it didn't take long until people picked up on this and asked the question, well, does this only apply to electrons, like in Heisenberg's thought experiment, or to the atoms that Dave Wineland is working with? Does it not also apply to larger objects? And a group in Vienna here, for example, set out to use larger and larger molecules with, thousands of atoms, and do another experiment with those molecules that shows a very quantum mechanical feature of, you could say, a superposition, in that it sends these molecules through a diffraction grating and monitors the arrival locations of these molecules. And the pattern that you get there for the arrival locations is only and best explained by saying that these molecules must have passed through different slits of this grating. So they must also have, when they pass through the grating, been at several places at the same time. So apparently this quantum superposition principle also applies to larger objects up to 1,000 atoms. And time hasn't stopped. In 2013 there are also some other experiments, and sort of people have pushed this to about maybe 1 million atoms or so that can be placed into these kind of superpositions. But still the question arises, where does this stop? Why are we never in a quantum superposition? Where is there at all? And if there is, where is the transition between the quantum world, where things are weird and we have this back action of the measurement and things can be in a superposition, and where things are the way that we expect them to be, very classical and well understood? Is there such a boundary? And some of the experiments that we are doing is, addressing this question, and we are really going not from 10 atoms to 100 atoms to 1,000 atoms, but we are taking something really, really big. You could say it's really human scale, namely membranes, of which you see a photograph here, that are about a square centimeter or so in size. So they're about the size of a fingernail. And these membranes, they are under tension, and so they vibrate like a drum skin. So this little defect here in the middle vibrates out of plane. And here's a picture. If we highlight the areas that vibrate a lot, we make it yellow. And you see that this is here, the central part here vibrates. This is about 100 trillion atoms. So this is really something rather large. And then we ask the question, okay, what kind of quantum mechanical features can we observe with such a device, which, as Søren mentioned, we call a quantum drum? And we do this, in the basement of the Niels Bohr Institute. There's gifted experimentalists, my colleagues. They use lasers. This little metal box that you see in the corner here is a laser that we pass through all kinds of lenses and mirrors, and then we send it through these fiber optical cables to the experiment where such a membrane is sitting. And the schematic looks like this. So essentially, we send laser light onto such a membrane, which sits between two mirrors that just recycles the light, so the light interacts more often with the membrane, and then the laser light comes out, and we measure the light here. And measuring the light here tells us something about how the membrane is moving. And here is a signal. This is what this would look like as a function of time. It looks a little bit random. It actually also is. But if we decompose this signal into its spectral component, so if we look at the characteristic frequencies at which this signal is oscillating, then we get such a very sharp peak, and that really corresponds to the characteristic frequency at which this membrane is oscillating. Similar to a guitar string that has a characteristic frequency at which it vibrates, this membrane also vibrates at a characteristic frequency, and this is this one here. And then we go and ask the Heisenberg question. So how precisely can we actually make this measurement? How precise can we make this measurement? And here you see again the peak corresponding to the membrane motion. And you see that our laser is already making a very precise measurement. So this level here would correspond to 1 femtometer, which is about the diameter of an atomic nucleus in 1 second of averaging time. And we see the peak here very clearly, and we see at the side of the peak we see this kind of background, and this is basically the imprecision of our measurement. This is somehow the blur in the sort of Heisenberg microscope picture. This is somehow the blur that we have. This is sort of our inability to really precisely see where the membrane is in any particular time. But then we can increase the strength of the laser, and we see that this imprecision goes down. And here I'm plotting the same peak again in a slightly different way so that I can see actually the size of this peak here more clearly. And then I see as the imprecision goes down, the back action actually makes the peak grow. So similar to the Heisenberg microscope, if I use more laser light, I actually perturb this system. And I perturb it in this case, a precisely quantifiable way. And if we do that, and we look at how large is the imprecision, how large is the back action of the measurement, and if we sort of multiply these two things with each other, never mind, the units and all that, we find that indeed they are also approaching a limit here, which is exactly the limit predicted by, Heisenberg many years ago. So also in these large objects, measurements are fundamentally limited. However, this is like nearly 100 years ago that this has been formulated. So, theorists haven't been sleeping over all these years, but they have also come up with sort of new ideas of measurement techniques where, we respect everything that Heisenberg thought of, but we still trick that fundamental limit. And so nowadays we know of techniques that allow us to break these quantum limits. And again, I don't have time to go to the details, but you see a few measurement traces here where basically each of these curves represent the uncertainty of the measurement in how this membrane is moving. And, according to a sort of simple-minded quantum physicist, this uncertainty should always be larger than this gray curve here, but it isn't. Sometimes we can make the uncertainty actually smaller. So we can beat these quantum limits using what we have learned about quantum mechanics over the last decades. And this has application for precision measurements. For example, one place where this is already applied nowadays are so-called gravitational wave observatories. So these are instruments that use laser-based measurement of the motion of large mirrors in order to detect what's going on in outer space when black holes are actually moving. They are actually shaking these mirrors here, and this becomes measurable on Earth. It's a new kind of astronomy, and they use these really tricks to beat standard quantum limit. Okay, now the other point about the quantum superpositions, that's even harder, you could say, and we know nowadays that one reason why it's not easy to create such quantum superposition states is that large objects are typically in contact with a lot of other degrees of freedom, which basically perturb the system. So in the case of our membrane, you could think of gas molecules that randomly impact on this membrane and give it a little kick, or some phonons, which are basically just some little vibrations inside the substrate of the membrane, which maybe also perturb the membrane, which leads to a situation where if I make repeated measurements of, say, the position and the velocity of the membrane, I find something else every time I measure, and this is somehow random. And in this case, if you have a coupling to other hot degrees of freedom, this membrane is not going to be in a pure quantum state described by a wave function, but it will be a so-called mixture. So it will basically be in any one of several wave functions, and we just don't precisely know which one. And this is then described by such a density matrix rho. And in order to overcome that, we have to do two things. We have to, first of all, eliminate the perturbations that come from all these environmental factors here, and this is something that we've gotten very good in our lab at. And second, we have to couple the system that we are interested in, like the motion of this membrane, to another quantum system that we have very, very good control over. And then we should be able to prepare the mechanical system in a pure quantum state. And this is an experiment that we have also done a few years ago. In this case, we use one of these refrigerators that you have maybe seen when people talk about quantum computers. And the way we go about that is that we take one of our membranes and we couple it to a superconducting circuit, which, if it's cooled to very low temperatures, a few millikelvin above absolute zero, is actually in such a pure quantum state. And then the coupling of the membrane motion and the superconducting circuit allows us to prepare the membrane in a pure quantum state, in this case the so-called quantum ground state. And we are by far not the only ones who do this. So here's an overview compiled by a colleague a few years ago of many experimental platforms, many systems that go from this single atom that I've talked about at the very beginning, all the way to some large, seriously large, LP size mirrors that weigh about 10 kilograms. And you see that people have applied these techniques to prepare them in a pure quantum state over this entire mass scale from 10 to the minus 26 kilograms to 10 kilograms. And you also see that the lighter the system is, the further down the error goes, and basically down in this case means a more pure quantum state. And so for these single atoms, actually we are very much capable to prepare them in pure quantum states. We're even capable of preparing them in highly exotic quantum states, like this quantum superposition state that I mentioned. And it's getting just very difficult for these large masses. But the community is making progress, and the work that we are doing is among the most massive systems that can be prepared in such a very pure quantum state. Very recently, there's also a very beautiful work coming out of Switzerland, of ETH Zurich, where they managed to prepare also a reasonably large object, a few fractions of a millimeter, in such a quantum superposition state, even if, so this is then a moving object where all the motion happens inside a crystal. So it's really a sound wave inside a crystal that is in such a quantum superposition state. Okay, now I want to take just, I don't know how I'm doing time, but I want to take 120 seconds to tell you a little bit about the applications of this. So one application of, back now to our membranes that we're looking into, is to show that coupling the membranes to other degrees of freedom could be a memory for signals, for quantum signals eventually. And we've done a proof of principle experiment here where we take a light field and send it towards the membrane, and we can actually store the light pulse as a vibration in this membrane, and we can later receive it very efficiently. And since we have done such a great job at isolating this membrane from these perturbing factors, we think that this could be in the future a way to build a quantum memory, for example, for a superconducting qubit. And another application in a very different direction is one where we exploit this exquisite sensitivity of these membrane resonators to forces, so our ability to make these very precise measurements. And what we do here is we place different samples like gold nanoparticles or these rods, which are actually tobacco mosaic viruses, on such a membrane, and then we scan a sharp tip over the membrane, and in this manner actually record an image of the objects that are on the membrane. You see here these rods, that's the viruses, and these spheres here, which are the these little nanospheres. And this is actually an approach that could lead to a novel imaging modality for single proteins. So we're actually also working towards imaging single proteins in this way, or even also other ways using this membrane. So, to sum up, if you remember from this talk 2 things, I'm happy. And the first one is the answer to the question, does quantum mechanics apply to the motion of large objects? The answer is, it looks like. So the experimental evidence that we have suggests that this is indeed the case. And on the other hand, what is this good for? Well, first of all, it deepens our understanding of nature, but it is also relevant for precision measurements of motion and forces and applications such as quantum memories and nanoscale imaging. And with that, I just want to show the people who do the hard work and thank you.